assume all of you got the mark last night. Okay. Focus for. I think almost all of you did well. I have no comments. So today I just handed in quiz number 5, which is the last one. So it's due on the 3rd of December. So take your time to do it. So that will be the last quiz for the semester. And you will of course have an exam in January. You will have a exam which will, I don't know the date for the exam yet, but normally it's on the around about the 20th of January. As soon as I know the date, I will let you know. I will also let you know exactly what contents will be covered in the exam. So you will receive an email from me about the contents of the exam. Okay, maybe in the next week or two. Okay. Okay, guys, I'm just waiting for other people to come to know. Boy, there are some few people missing. I will let you know later. Yeah, later. Your friends coming? They're coming. Only one? Okay. Maybe. Oh, you got one already. I don't know. You got one. All right, guys. Let's begin. I want to begin by summarizing what we did yesterday. Okay, yesterday I talked about I talked about the GEV method. I talked about the semi-parametric estimation methods for VAR. One of them is known as the GEV method. One of them is known as the GEV method, which is as follows. And the estimator for VAR under this method is given by this. And this is semi-parametric because there are 3 parameters in this formula. 2 of them are estimated parametrically. And the third one, which is the psi parameter, is estimated non-parametrically. Right? Okay, guys. And then I talked about the second. Of the 2 semi-parametric models, estimators. And that one is known as the GP method, or the generalized Pareto method. And for this one, the estimator for VAR is given by this formula here, right? And in this formula, there are 2 parameter estimators, sigma hat and psi hat. Sigma hat is estimated parametrically, and psi hat is estimated non-parametrically. And therefore, this estimator is a semi-parametric estimator. Okay, and then I talked about the proofs proofs of the first four properties of ES. The first one is the translated property, which I proved here. Second one is the first one is the, not the translated, the normalized property, which is, the proof is here. And the second one is the translated property, and this is the proof of it. And the third one, sorry, what did I do here? Yeah, the third one is the monotonicity property, which I proved over here. And the fourth one is the positive homogeneity property, which I proved over here. Okay, all right, guys. So those are four proofs, and the proof of the subadditive property. I haven't given you given the proof of the subadditive, but I think I sent you a link sometime 2 weeks or 3 weeks ago. I sent you a link for the proofs for the subadditive property of ES. So if you look at that link, there are several proofs of the subadditive property for expected shortfall. But next, I talked about the estimation methods for ES. There are three groups. One is parametric estimation methods, non-parametric, and semi-parametric. Okay. And the next one, starting with the parametric, I talked about the normal distribution method. Under this, the estimator is given by this. This is the estimator for the normal distribution, right? Okay, and the second one is the uniform distribution, and under this, the estimator for ES is given by this formula. Okay, and the third one is the power function distribution method, and under this, the estimator for ES is given by this formula. And the fourth one is the variable distribution method, and under this, the estimator for ES is given by this formula here. This is the formula for the estimator for ES for the variable distribution method, right? Okay. Now then I started talking about the non-parametric methods. The non-parametric methods for estimating ES. The first one is the historical method, and the formula for that is this one. This is the formula for the historical estimator for ES. Okay, and the second one is the bootstrap method, and the formula is this one here. Okay, and the third one is the jackknife method, and this is the formula for ES. This is the estimator for ES under the jackknife method. And the fifth one is the kernel estimator for ES, which is given by this formula here. Okay, I know it's a complicated formula, right? And number 6, sorry, is it number 5? Number 5, the fifth one is the Richardson method, which is actually if you looked at it yesterday, the picture in front of this room is the guy, Professor Richardson, right? So it's named after him. And under this method, the formula for ES is given by this complicated expression. It's not really complicated, because what we have is a determinant of a matrix divided by a determinant. So determinant of one matrix divided by a determinant of another matrix. I'm sure you know how to compute. There are programs in R, for example. In R, there are functions for computing the determinant of a matrix. Right, so you can use those to compute this, right? Okay. Okay, guys. So those are 5 methods for estimating ES non-parametrically, right? Now, what I'm going to do today, I'm going to finish off. Let me see where I am. I'm going to finish off the estimation chapter, right? So I'm going to start with okay, C. By the way, is my writing clear enough, or is it? Can you see it? Because I'm partially blind, so I can't. That's why I brought this one, because I can't see it. Sorry. So that's why I keep asking you whether you can see my writing or not, because I can't see my writing actually. I can't see my writing when I write it. So anyway. If you can't see it, let me know. All right. The last section of this chapter. Sorry, can you see it now? Okay. The last section of this is the semi-parametric estimation methods for ES. All right. And the first thing I'm going to talk about is there are two methods. All right. The first method, I'm going to call it simply method 1. Okay, method 1. Under this method, right, suppose x1 to x2 are losses, right? Then RT defined as the difference between xt and xt minus 1 are the returns, right? right? And you say a process. I mean, what I have written here, guys, is a definition of a heavy-tail process. I don't know whether you know the term heavy-tail. You might have heard from other courses you have taken in the past. But this is what the definition is. This is what I have. Okay, let me put it in a box so that you can see. So what I have written down, basically, this box here. Sorry. What I have written down here is the definition of a heavy-tailed process, right? A process is said to be heavy-tailed if it satisfies the conditions listed in this, where the tilde here means behaves as. So this symbol here means behaves as, right? So this is equal to, it reads as behaves as. Okay, that's what it means. All right. Okay, you get what I'm saying. I hope you can see this. Okay. Now, if okay, if the process RRT is heavy-tailed according to the definition that is given here, right? Then the estimator for the expected shortfall is as follows. So the estimator for expected shortfall is given by the following formula. It's equal to 1 over P times the integral from 0 to P of exponential in big bracket L n comma P divided by n times Q. Okay, and just give me a second. It's gonna be a big nasty expression. 1 divided by alpha and the whole thing multiplied by R L N P. You don't need to write this down, guys, because I will, as you know all the time, I will post this online after the class. So okay, so this is the expression for the expected shortfall, where well, ln P is equal to the integer part of this, right? And the alpha hat, excuse me, sorry, alpha hat ln is equal to the following: 1 divided by L summation I from 1 to L of log Ri R L in brackets, close the bracket, and then take -1. And finally the R1 to Rn are the order statistics. In other words, R1 is the smallest return and Rn is the largest return. Okay, so I don't know whether you can see the whole thing or not, but it is complicated. But so the first equation, the first two lines of the screen give you the estimator for ES, right? And where ln p is defined as the integer part of n times this, and alpha hat l comma n is defined as this, and these numbers are the ordered values of the returns, right? Are you guys okay with this or not? I know it looks complicated, but I would not expect you to know this for the exam. I mean, if I ask you this in the exam, I will give you the formula and ask you to apply it, right? But I don't expect you to know this. Only know how to apply it. And once again, under the exponential sign, we have ln p divided by nq, and the whole thing raised to the power 1 divided by alpha subscript ln comma p comma n, where alpha ln is defined by this, right? And that thing is multiplied by this, and the integration is with respect to q from 0 to p. Okay, right, so that's the first method. This is a non-parametric method. The second non-parametric method, which I'm going to talk in a minute, is as follows. You guys have any questions? You should. Feel free to ask me questions if you have. The second method, so it's going to be number 2, which I'm going to call method 2. Okay, for this method, it works like this. So under the same assumptions of method 1, under the notations of method 1, the second semi-parametric estimator for ES is given by this. Excuse me, I'm having difficulty seeing my writing. That's why I keep plus or okay, this is the formula for the expected shortfall under the second method, where gamma hat the formula for gamma hat is as follows. So gamma hat is 1 over k, 1 over k times sum from I from 1 to k of log then r n minus I plus 1 divided by r n minus k. Okay, and k is a number between 0, 1 and n. K is a number between 1 and n. Okay, so these two are this method, which is method 1, and this is method 2, are both semi-parametric estimators for expected shortfall. Okay, so that completes the chapter on estimation. And if you want to know more details about all the estimation methods I've talked about, you could refer to the printed notes I gave you. I'm sure I gave you copies of this, right? I'm sure all of you have a copy of this, right? So if you want to know more details, you can look up in the printed notes. But for the exam, you only know, as far as the exam is concerned, you only need to know what I have written on my handwritten notes, right? You don't need to know anything from the printed notes for the exam. Okay, you only need to study the handwritten notes for the exam. Okay. Any questions so far, guys? Hello, guys. No questions? All right. So I want to start a new topic today, if you may allow me. The topic I'm going to start today is called copula, right? This is a new topic for the course, right? Okay. Okay, suppose you have a random vector x comma y, right? Right, there are many situations in real life where the two variables x and y will be dependent on each other. So some examples. Example 1 could be that x okay, example 2, this is, did I say example 1 here? Example 1, yeah. Example 2 could be where x comma y is equal to oil price food price. Okay, so these are just two examples where a change in one of the variables will affect the like if the oil price goes up, the food price will go up, and similarly if the oil price goes up, the price of a car will also go up, right? Okay, so in these two examples, clearly the two variables are highly dependent on each other, right? And a copula, well, a copula is something that you can use to describe the dependence. So let me so the term copula, a copula can be used to describe the dependence or to model the dependence among two or more variables, right? Okay. Now, where am I? The next thing I want to talk about is the following. Okay. Let me put this here. Okay, suppose the random vector x comma y has the joint CDF f x comma y. I think I talked about this notation before in the class, I think. So capital F x comma y denotes the joint CDF, and these two guys here denote the marginal CDFs, right? Okay. statement 1 says that for every joint CDF there is a corresponding copula. Now, before I prove this statement, let me go back to the previous slide. Let me go back to the previous slide here, where I said a copula can be used to model the dependence between two or more variables. Right? I should have said something. For two variables, okay, when you have two variables, a copula is denoted by C. Capital C is a function from this space, which is a unit square. I mean, what you have here is a unit square, right? To a interval, to a unit interval, right? So when you have two variables, copula is a function from the unit square to the interval, and it has the following properties. Right, which means this is right. So in a two variable case, a copula is a function from the unit square to the unit interval with these properties, which means that the marginals of C, the marginal CDFs of C belong to the uniform distribution. That's what these two tell you, right? Okay. Okay, now let me go back to, I'm sorry for switching, but let me go back to the next slide, which was this one, right? So what I said here, guys, is the statement number 1, which says that for every fx comma y, there is a corresponding copula. Now I'm going to prove this statement, guys. I'm going to prove it. Okay, so to prove it, we know that fx comma y, where by definition is equal to the probability that capital X is less than or equal to little x and capital Y is less than or equal to little y. Yeah, you know, I mean, this is the definition of the joint CDF of any bivariate random vector, right? Okay, now this you can write as excuse me. You can write it as this, right? Okay, now can you tell me, I know you've done statistical inference and all the courses, can you tell me about the distribution of this and this? What distribution this has and this has? You must know this from any ideas? Haven't you seen this before? I mean, when you take the CDF of a random variable, what does it give you guys? You haven't seen this before? Okay. Do you know the fact that when you take the CDF of a random variable, what you get is the uniform random variable. It's known as the this is known as the probability had you heard about this term before? The probability integral transform, which says that you should take the CDF, you should have a variable x, right? And fx is the CDF of x. Then fx of x is a uniform random variable. You seen that or no? Yes? Okay, so that's what I have used. From this line to this line, I have used the probability integral transformation, right? Which is which you might know or might not know. If you don't know it, just try to remember it. Okay. So what you have. So I'm gonna call this u. I'm gonna call this v. So what you have is that the probability that the u is less than or equal to fx of x and v is less than or equal to fy of y. And this is, and u and v are uniform random variables, right? And therefore you can write this as C, because remember, on the previous slide I said that C is a copula is something defined on the unit square with uniform marginals, right? So you can write this as C of fy of y, right? Okay, the proof is complete. The proof is complete. Did you understand the proof? I just want. Did you guys understand the proof or not? So all I have, what I have used, the tricky part here is to use the probability integral. So you start with the joint CDF, which is defined by this, and then you apply the probability integral transform to the left and the right. Left and the right, you get this, right? And at this point, you should realize that these two guys here are uniformly distributed because of the probability integral transformation. These two are uniformly distributed. So this has the uniform distribution, and this has the uniform distribution too, right? And I call this U and I call this V. So I go to the next step, which is what you have here in the top line is the joint CDF of two uniform random variables, and therefore it must be a copular, right? Okay, because as a minute ago I told you a copular is something which is defined on a unit square with uniform marginals, right? And that is exactly what you have here. Okay, is that clear, guys, or no? Why are you keeping quiet, guys? Is that clear? Not if it's not clear, let me know. You okay? Come on, guys, please. Why is it? Are you guys okay? Yes? No? Then if it's not clear, let me know. I'm happy to explain again. So that's statement one. Statement two. Statement 2 is the following. So let me go back to statement 1. Statement 1 said the following: for every okay, and I'm going to prove this. All right. So for every copula, remember capital C denotes the copula. For every copula, there is a corresponding joint CDF with of two random variables x and y. Okay. So I'm going to show you how to prove this. So you start with U, yeah, which we know is the yeah, because by definition, as I said, by definition, the copula is the joint distribution of two uniform random variables. Right? Okay, now we know that just a minute. Let me call this capital U, right? Let me call the first one capital U, and let me call the second one capital V, right? Now I'm gonna You see what I've done here? You see what I've done? I have applied the inverse mapping of fx, right, to both sides, and the same thing, the inverse of the CDF of y to both sides of this. Now let me ask you, what do you know about this? This is what do you know about these two? Have you seen this before? Don't tell me you don't know, guys, please. Why are you keeping quiet, guys, today? I will give you chocolate in a minute. I've got some chocolate. Well, what do you know about these two guys? Huh? This is equal to x. Do you know that or not? That's once again, this step here follows because of the probability integral transformation. Okay, right? That is, I don't know whether you've seen this before. If you have a uniform variable and you take fx inverse of that, what you get is the random variable x. Haven't you seen that before or not? Yes? Hello, sir. You okay?
Yeah.
You seen it?
No.
What about you guys here? You've seen this result that if you take the fx inverse of a uniform variable, what you get is the random variable x. No. It's known as the probability integral transformation, right? Okay, and come on guys, just smile a bit. Come on. So you have a joint CDF of xy at you look. Okay, so we have proved. So the proof is complete once again. So we have proved. So what we have proved, guys, is that starting with the copula C, you see we have started with the copula C, which is above the line. Okay, sorry. Let me bring it down. We have started with the copula C. C is a copula, and we have proved that C, a copula, is equal to the joint CDF of two variables x and y, right? Alright, so it proves that. So this is the proof of the statement number 2, right? Okay, is that clear, guys? So the proof. Let me write it down. The proof is complete. The proof is complete. Okay. The next thing I'm going to do is we have I will finish at 5 o'clock, then we can move to the next row. Okay. The next one